Bismillah ar-Rahman ar-Rahim. Today we'll have first lesson 1.1 for grade 7 chemistry, matter and energy. Kinetic theory of matter. All matter is made up of atoms and molecules that act as tiny particles. As you see here, the atoms are making up the matter. These tiny particles are always in motion. State of matter depends on its molecular motion as measured by temperature. The higher the temperature is, the more the motion of particles are, and the lower the temperature becomes, the lower or the less the motion of the particles that we have for the matter. As you see here, compared to the previous slide, the particles of matter here are moving because there is a heating or a raising in the temperature of this matter atom. At the same temperature, the heavier particles move slower than the lighter. The heavier ones move slower than the lighter particles. We have 4 states of matter. As we have done this from before the previous years, we've got solid, liquid, gas, and the fourth one that we will not discuss it for this lesson, but you may have some extension for it later on, which is the plasma state of matter. Solid. The particles are held by intermolecular forces, bonds between molecules. Particles of solid are tightly packed, vibrating about a fixed position. In other words, they don't move out of position. Solid have definite shape and definite volume. Okay, here is the solid particles, and you will remember or you will notice that they are in vibration, but no much significant movement for the particles. Example is, as we have here, the metal, a diamond. Okay, let's move to the next part, which is liquid. Particles of liquids are tightly packed, but are far enough apart to slide over one another. Intermolecular forces have weakened. So in the case of liquid, the intermolecular forces is much less than in solid case. Liquids have an independent shape. It means their shape is going to be changeable, and a definite volume. So liquids take the shape of whatever container because the shape is changeable. They're going to take the same shape of the container they are in, but they cannot be squeezed into a smaller volume. That's why we say it has, or the liquid has, a definite volume. So it cannot be squeezed easily into a smaller volume. That's a very important point to know. Okay. Let's study how the particles are moving in liquid. And then we've got the example, mercury, and any solutions that we have in the lab. It's an example of liquid. Gases. Particles of gases are very far apart and move freely. Intermolecular forces have been completely broken. Okay. Gases have an indefinite shape and indefinite volume. Particles are not close together. They can be squeezed into a smaller space. For example, pumping up a bicycle tire. See how the particles of gas are moving? See how much intermolecular space we have? And obviously the intermolecular force is such a weak force that the particles are moving freely away from each other. An example of a gas. Okay. Okay. For the fourth state of matter, as I said, we will talk about it later on, not in this aspect. Compare the movement of particles of solid to liquid to gas. Here is the particle arrangement, and also you can notice the particle energy, how much they move, and the particle to particle distance. Okay. Phase change: melting and freezing, boiling, evaporation, condensing, sublimation, evaporation. The melting point: change from solid to liquid and liquid to solid, is going to be explained in two aspects. Same temperature, if melting particles are gaining energy, if freezing particles are losing energy. Okay, so we will say a melting point is going to be for a solid, it will melt to become a liquid. The same point is going to be assumed as a freezing point, but for the liquid in order to freeze into a solid. It's a one certain point. Okay. The stronger the intermolecular forces, the force that connects or bonding the particles of the matter together, the more energy needed to weaken the intermolecular forces. Okay. Therefore, higher melting point temperature. So in case of intermolecular forces, the most state of matter that has the strongest intermolecular forces is the solid. So we will need more energy to weaken this force, break it down, and make the solid melt. So higher melting points temperature, we will get higher melting points for this solid. During the phase change, the temperature remains constant. Okay. If we will see later, the graph will show you a flat horizontal region on the phase diagram. But after all the sample has changed phase, the temperature will change. The boiling, which is a change from liquid to gas, and the condensation, gas to liquid. Again, it's the same point. It's going to be the boiling point when the particles are gaining energy from a liquid state to a gas state. We will get the boiling point in the middle. If the particles, they will have condensing, so the particles of gas is losing their energy and they're returning to a liquid state. Again, the stronger the intermolecular force, the more energy needed to break the intermolecular forces. Therefore, higher boiling point temperature, and here also, yes, so it's going to be the same point, boiling point and condensation point. During the phase change, the temperature remains again the same, which we will have a flat horizontal region again on a phase diagram. After all the sample has changed phase, the temperature will change. Sublimation, changing directly from a solid to gas, also changing directly from a gas to solid. There is no liquid state in the middle. Okay. Evaporation, liquid to gas, but not necessary at the boiling point temperature. We know that changing the liquid into gas, we will have the boiling point in the middle, but actually evaporation starts even before the boiling point of a liquid. Some particles gain enough kinetic energy, heat, to overcome the force, the intermolecular force, and becomes a gas. So the top particles, they gain more energy, they're going to lose the intermolecular force and escape from the liquid. This is where evaporation takes place. Remember, temperature is a measure of the average kinetic energy. Thermal expansion. Matter expands as it gets hotter and contracts when it cools. Exception, water actually expands when it freezes. So generally the matter will expand when it gets hotter, okay? And it contracts when it gets cool. But there is an exception. When I have water and I'm going to freeze it, I will have I will notice that it's going to be expanded due to locking of hydrogen bonds, which is an exception. We can just study which example is the opposite or which one is the exception. Okay, expansion joints on bridges turn hot water over jar lead. That's an example of the classical thermal expansion. When I have a jar covered, a jar lead, I'm going to just pour some hot water. The lid is going to open easily. Why? Because it expanded. Okay, because the gaps in the sidewalk are going to loosen.